Okay, so today we are going to talk about electronic structure. Yeah, and here is the molecular Hamiltonian. Um, they choose some normalization. So usually there's maybe a factor of 2 connected energy for ion or nuclei, and electrons and nuclei and electron are interacting with Coulomb force, and electron, they're also interacting among themselves, and then this is the interaction of the Coulomb among the nucleus. Okay. Yeah. Yeah, this is the so-called Born in the so-called Born Oppenheimer approximation. So yeah, to deal with the electronic problem, and the nuclear coordinate would be entering as a parameter. So you assume that you the light is about to turn on, so I need to move. Yeah, so this assume that the nuclei are heavy, so electron will probably move together with the nuclei. And so that there's a reduce in that, so-called, approximation, Born Oppenheimer approximation, then you would just deal with the electronic part. So this is the electronic part, and electron interacting with the nuclei, electron interaction, right? And you want to know the ground state energy, ground state wave function. Yeah, this problem is difficult, even just writing down this. And if you have random potentials, well, you could also have random potentials. There's a V of R. This actually I think it's hard. It could be NP hard, could also be as hard as QMA, depending on, the problem, the randomness, etc. And yeah, probably if you're not in physics, you probably uh don't know much about this. But even if you're in physics, you're not studying like condensed matter, probably you have never seen those. Yeah, so to solve the simplest problem is called Hartree-Fock solution. It's a way to approximate the ground state wave function by some kind of product wave function, but you need to take into account of they are fermions, so they're anti-symmetrized. Yeah, so this method approximates the n-body problem, n one-body problem. So the electron would move in the field of others, so it's like a mean field approximation. Yeah, yeah. So there are a lot of things behind this. Probably it's hard to justify just telling them in just one class or maybe a fraction of the class. But there are actually packages to solve this using the Hartree-Fock method. And certainly there are more complicated methods to improve the Hartree-Fock solutions. So what we're going to have is we're going to write the electron Hamiltonian in this second quantized form, and these HPQ representing the coefficient that derive from this Hamiltonian in some approximation or Hartree-Fock approximations, and you calculate what is they call one body turn and two body turn. So A dagger A, imagine it's like annihilating from Q. Q could be a momentum orbital position. So you annihilate the from and make it appear in P, so it's hopping. And this is interaction term. You can imagine you have an electron comes in with S, another comes with R, and they sort of interact and go out as Q and P. Yeah, so this is called one-body integral for this expression here. This is the two-body integral. So you can see that the first two come from the first two turn in the electron Hamiltonian, and the last one come from the interaction among electrons. Okay, so yeah, so then you solve the wave, in principle, you diagonalize this, and you want to find the ground state wave functions. Okay, so this phi is some kind of basis, some orbital. So this just use some particular basis. Okay, so yeah, as we mark here, these molecular orbitals can be occupied or virtual unoccupied. Yeah, and because each electron has spin up and down, so each molecular orbital can contain two electrons. When they call spin orbital, they're assuming, okay, they're labeling it as, for example, alpha is spin up and beta spin down, so you only occupy one spin orbital. Okay, so when referring to the number of orbital, we'll be using the number of spatial orbital. Okay, so spatial orbital times 2 will be the spin orbital number. Okay, so that's the background, but this probably is the central part of condensed matter physics, and then how they approximate that, and in solid, and yeah, not in free space. But we'll take this as the initial starting point, and there are packages to compute these one body of orbit integral and two body integral. Okay. With that, so here is the package show how you obtain a initial Hartree-Fock solution. Basically, Hartree-Fock solution, as I said, is a mean field assuming the effect of all other electrons or nuclei are sort of a external field, and you solve it and solve itself consistently. It becomes a one body problem, and you got an orbital phi, right? So you solve that using the package. And then once you have these phi, you can just do the integral. And this will be done by numerics for these packages. And Qiskit is interface with different classical drivers that can find the Hartree-Fock solutions. Okay, so it's already built in. It says there are 3 that are available: Gaussian, psi4, pi, SCF. Yeah, so here they're setting up a pi SCF driver for the hydrogen molecule. Okay, this is at some equilibrium. So the way you write is you write what kind of atom you would have. So hydrogen at origin, so 0, 0, 0. Hydrogen, another hydrogen at 0, 0, 0.735. And this is using the unit angstrom. So you always have some convention, but you need to know the unit. And they choose some kind of basis of the wave function. It's called HTO3G. And okay, this charge neutral, so they want to find the state has no charge and no spins, meaning a singlet. Okay, so they're setting up a driver for a hydrogen molecule in equilibrium. Okay. Okay, they said that here unit is angstrom. So basically, you just need to run this, and most of the time, you are changing maybe the coordinate, and you want to try other orbital basis. Okay. No module. Did I? Okay, let me make sure that I installed Qiskit-Nature. So you would do a pip pip install Qiskit-Nature. I'm installing real time. Okay, so let me run again. Okay. Oh, we also need to have ISCF, so we need to install that. See, maybe we could just do pip install ISCF. Maybe let me make a remark here. Make sure you install required packages. Install CF, install Qiskit-Nature, something like this. Hopefully I have that now. Let me see, still install. So maybe let me start my kernel again. Again. Okay, if I cannot install in real time, I'll just go over the notebook without running it. Okay, now it's done. Okay, so it says running this driver will get a electronic structure problem. Okay, so this is running this. Okay. Qiskit-Nature's representation of electronic structure problem. Yeah, this is for this. So if you want to know more about that, then this is this here. There are base class, vibrational structure, electronic structure. So using the electronic structure here. Okay. Yeah, for those who join later, I basically just describe these electronic structure problem as a general Hamiltonian. And you don't need to worry about this. I mean, just need to have a sense of what's involved, electrons and nuclei interaction. And this second quantized formalism, you have seen the A dagger, C dagger, A C in last semester's QS course. Here, these are just electron annihilation creation operator. All you need is these coefficient, and you set up a Hamiltonian, and you will then turn that into a spin Hamiltonian. Okay, this is a package by CF is to compute using some basis. You rarely don't need to change this when you play with this. You can change, maybe there's some 6G, but yeah, different bases, molecular bases. Okay, so let me see, did I run this? Okay. So we have an electronic structure problem. And this here talk about the electronic structure problem and its component. Electronic energy Hamiltonian. right? So the most important is this Hamiltonian. So basically we're getting this Hamiltonian here. Okay, so there's a class electronic energy. This class is able to generate second quantized operator from the one body and two body integral. So once you have run this, you have these one body, two body integral. Okay, so Hamiltonian equal to problem. That Hamiltonian problem is what we already set up here. And then you say coefficient and Hamiltonian dot electronic integral. And then you print coefficient. You print coefficient from, let's see what coefficient. They're printing the alpha. So this coefficient is an object of electronic integral. Basically, this one and this one here. So next, what you do is turn them into a second quantized operator. Basically, this is this one here, this one. So you have dagger, no dagger, 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 no dagger, no dagger. So let's see what it's print out. So this is fermionic operator, as I said, a number of spin orbital 4. So basically there are 2 orbital and each has 2 spin. Number of turns, there are 36. So there are 4 orbital, right? So this subscript 0, 1, 2, 3. These indicated the orbital. Plus, plus, minus, minus, I think it's representing dagger, dagger, no dagger, no dagger. Okay. Okay, and so these above are for A dagger, A current, and this is like 2 body. So these are 2 body, and this is 1 body, A dagger, A, and these are the coefficient. So basically running this code here allow you to turn this electronic problem into a operator, which is the so-called second quantized. Yeah, and all the coefficients are sort of built in here inside its coefficients.
It's interesting why all the coefficients looks like real numbers.
Real number, let me see. It could be the basis that they use. Yeah, and this is like a grounds. Maybe this is like really singlet, and I don't know. But I think it's probably the particular orbital we'll choose. STO3G. Yeah, different orbitals. But but these are real numbers. They're all real. If you have more complicated molecule, you might, and it also depends on them. You can look at the maybe STO3G. 3G. There's STONG basis. The minimum basis set in quantum chemistry. Slater type orbital and Gaussian. Gaussian. Okay, this Gaussian and Slater type STO. 3G would using 3 Gaussian. Okay, 2G. So 2G will be linear conventional, 2 primitive Gaussian. 3G is linear combination of 3 primitive Gaussian. So maybe the coefficient they're using really real coefficient alpha 1. So these alpha they are particular meaning, like it was printed previously. I'm not sure whether they're same alpha or alpha coefficient. Right, I think it's because it's using Gaussian and Gaussian integral, right? So if you look at, okay, if you look at Gaussian and you come back to here, Gaussians, if you use real coefficient, this will not give you anything that's complex because all these are real. Right. Maybe, let's see, STO NG orbital with complex coefficient. See if well, I don't get complex in all these. This is what we just saw. Yeah, I suspect it's really basis dependent. So this is the basis they chose.
Okay.
Okay, so yeah, so there is the comment that this is purely electronic part of the system. Right? So here we have these edge electrons, but we start with a system that has everything, and you reduce down to here, but there are also the nuclear part. So the nuclear part is not included there. Oh, so the classroom is also going to shut down its lights. Stand up and move. Okay. So it's here. So when you calculate this Hamiltonian, they also record the nuclear repulsion energy. As I pointed out, it's this part, the nuclear repulsion. Okay. Because it's a constant, assuming then the nuclei are heavy and they don't move. So they are just parameter. So but the energy is there. So this is nuclear repulsion energy. So this is not included in the second quantized. Okay. Okay, it shows what is the additional information. Molecule. Okay, this is symbol HH, right? Coordinate, multiplicity, 1, charge 0. I think this probably represent the spin 0, so multiplicity is 1 unit. Okay, because unit is 4, but I thought it's Armstrong. Okay, mass. Okay, reference energy. Exactly, the reference energy, we can see if there's any documentation. Energy. This is from AI, so okay, see as anything. Reference energy is the energy when all electrons are ionized and nuclei are infinitely separated. Effectively a zero energy reference point. Okay, this is the convention even for periodic calculation. Okay. Yeah, so maybe, I mean, this is really just this package. I don't want to go into too much detail. There's a lot of documentation. As I said, everything I said here, this could be expanded to like a few lectures. But since we are just, our aim is just to use it. Yeah, so I think this is nice introduction about a lot of background, basic information about ICF. I know maybe if you are doing chemistry calculation or condensed matter, then you would probably use this package. But again, also other band structure calculation, you would use other packages. Yeah, since this semester we don't have anyone from chemistry, but otherwise it will be we'll we'll have some interaction with people from chemistry. Okay, so there's this reference energy and okay, number of particles, one. I think one is in one orbit away. One is one spin species. One. You have one up and the other down. Number of spatial orbital. Yeah. Phases. Okay. Additional observable. So this class electronic structure problem also have additional. They call it factories. So there are other property. You can say particle number, angular momentum. The particle number. There's number of particles. This is from this. This is somehow they have places in the problem. There's number of particle, and also in the property there particle number. Momentum, excitation. But somehow why it does not print the values, or maybe yeah, I don't know why it doesn't print. It's an electronic property container. Maybe nothing is there yet. Okay, so me stop the live on. Turn off. Look like every 10 minutes they're checking if anyone's moving. Okay, so I guess this it says this is container, so maybe at this point, there's nothing there. Yeah, if you want, you can always go look up. Yeah, I don't know how much time I would spend looking up. This is electronic. We're looking at this electronic structure driver, right? And then we return electronic structure problems. And this class is here. If you want, you can go to properties. Yes. Search properties. Property, a container for additional observable operator factories. Okay. Yeah, to know that you need to see what electronic property container contain what. Okay, perhaps let's not do that unless any of you feel that's really urgent. Yeah, I don't intend to go in so much detail. So solving this electronic structure problem, we can use classical method. For example, I think that's what they are doing here. Import numpy minimum eigensolver. Okay, this here also second quantized algorithm ground state eigensolver. Mapping use Jordan Wigner. Okay, so just define the solver and you solve it. And you print out the results. So it tell you the electronic ground state energy. This is using algebra file. You get this computed part. And as I said, is they tell you the nuclear repulsion energy previously, and you add them together. So that's the total ground state energy. That's the total ground state energy. Well, this total Hamiltonian, we're under some approximation. Okay. So there are also other information, measure observable, okay, particle number, S total spin, mass. Wait, this is magnetic moment. Okay. And dipole moment. So maybe here we can see if these print out to get something. Else. Okay, so I want to see if we but problems. Yeah, but I don't know whether you would update. I would update that. Oh, okay, so below. Wait, we should have the particle number. How do I print it out? Example one, print out angular momentum. Maybe they have. Not so helpful at this point. The class angle momentum. is property. Okay, print. There is overlap. If it, does it have something like open? Can I do this? Type non-object type, not callable. Okay. But these are information we have. Maybe see what the result is. Okay. Perhaps when they solve, maybe they don't change the problem. They just things will just collected to the result. Okay. I cannot say for sure because I'm not an expert in this. Okay, but this is solving the electronic structure problem, and you see it's using the non-polynomial eigensolver. It's really not quantum. So you could replace this by like a VQE, VQC circuit, etc. Let me see the next one. This is the second notebook that I uploaded. This one is for the vibrational structure. So yeah, the Hamiltonian is the same, and then you are interested in the vibrational mode, and there will be angular momentum. Let's see, it's not. It's more like a spring with some lowest energy, then you sort of expand that as a harmonic oscillator, and that's the mode. Yes, for the angular momentum, that would be related to the rotational mode. Okay, so they need to expand this potential. Okay, so in the end, what you need to have these coefficients. And so I guess you would have drivers just using Gaussian force driver. To import bases for vibration, it's probably easier to use these harmonic bases. And for detail, I don't know exactly the detail here. Okay, but there are really already standardized procedures for you to map. You have defined the basis and the driver, then you get a vibrational problem. Okay, there's also the truncation order, like there's this potential to what order you truncate. And then you turn to the second quantize. Really similar to the previous one that we spent quite a lot of time talking about here. The second quantize, basically you have these dagger, non-dagger, etc. operator. Okay, and then you diagonalize that. So you print out the operator, I can see the operator. Okay, so 0, 1. There are two, so each has two labels. So this labeling the orbitals. They call it models. So models is the number you put in here. the basis. Okay, so dagger, no dagger, dagger, no dagger. This is four operator term. Dagger, no dagger, dagger, no dagger. Yeah, so you can turn that into a spin problem. Like so here is turning to the spin problem. Qubit operator. You can, for us it is very easy to visualize why these are the Hamiltonian with spin operator. Actually for the previous one, we never print out. This is the previous one. Mapping. Okay, it does not directly map the problem to spin like explicitly. It's embedded in the software. Right here, you are using this. You could probably do this direct mapper, but we probably need to have imported somewhere today. Here is the map. Here. Right. So if we use the same, let me see if we have that in the first one. We don't have. Don't remember we have that imported. It's not. So, but we could check this Hamiltonian. This one. This one we can do it here. Oh, Qiskit-Nature second quantized matter, direct matter. And operator. This is this second quantized. So let's please. Right. So this one is also a qubit problem, right? This is Z operator, X operator, YY. Okay, so this is to show it in this poly basis. Okay. Yeah, even if you don't have full knowledge of the background, like I also don't, you can still play with the code. And you can see the next one they would do would be, okay, solving that. Oh, this is actually more than how many qubit is 1, 2, 3, 4, 5, 6, 7, 8 qubit. Yeah, so this is in principle is a much harder problem than the previous. Okay, this so this is just to have change the number of models per mode. So this is probably changing this 2222 to something else. Okay, and then it will have more. Just changing to 3 truncation, second order. Yeah. Okay, there. This and then solving that. Okay, how many qubit we have? 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, they're more than so the number of modes you models in each mode you use would change the number of qubit. Okay, this is to Okay, they change it back to 2 to 2. And to solve that, you will need to say what is the mapper, right? This like in the electronic problems using Jordan vector is using Jordan vector to solve that. To do the mapping, and then you use these numpy. Okay, numpy minimum eigen solver, and then you bring results after you solve that. Okay, the vibrational ground state energy is this. Okay, using inverse wavelength, number of occupied models for each mode is. Yeah, so this is still classical, and this one, the third notebook that I uploaded, I think it will show the quantum one. Okay, so you don't need to worry about the detail now. You already know the structure, right? So you set up some driver from the pi SCF. Again, this is still hydrogen molecule. Okay, the same. This is the same one that we had in the first notebook. Okay, you do the mapper. This is now Jordan vector, and if you want, right, you could also print out this the Hamiltonian. We did it here. You could also do that. Now the solver, we already see that they use NumPy minimum eigensolver. Okay, so they say to find the ground, we could also use VQE. So they would here initialize a VQE, importing this package. This is classical optimizer, and you use this estimator class primitive. Okay, and from this circuit library, you import algebra file. You see CSD. This is one that's very common in quantum chemistry. CSD. So again, you will need to say a few things about the problem. This is number of spatial orbital, number of particle, mapper, initial state. Okay. And this is a VQE solver, ansatz. So you set up this ansatz. We can print out the ansatz. Okay. Ansatz that maybe we decompose and then draw. Okay. You see that this is the circuit, and there is this parameter here, another parameter. So there are 3 parameters in the VQE. Okay. Okay. It says one could also use other ansatz. It's using 2 local. Yeah. This is another solver. We could also print out a 2 local circuit. T1 is a TL to TL circuit. We found a circuit. This is it. Oh, maybe. Compose. Okay, I don't know why we don't see anything here. I think it should be the correct. Otherwise, it should be a error, right? Somehow it does not show to local. Yeah. Yeah, I know. I have no idea why it does not print out the circuit. Right. And this is setting up to compute that import ground state eigensolver. And then you will need to have the mapper, for example, Jordan Wigner, or other parity mapping, and we don't have time to talk about that. Solver. So VQE solver is the first one that we define here. And you do that and solve it. They will tell you the electronic ground state energy, computed power. So the format is the same as the classical output, but it's using the quantum part, the quantum circuit variational circuit to do that. And compute this with a NumPy solver and compare the results. Okay, so electronic ground state minus 1.85 is here is 1.85, 72.5. It's almost identical up to the last few digits. Okay, there's also other things. So here it's using, well, for you, you could probably say, okay, I want to compare with another solver. You could also do this. Another solver. Okay, and you can compare the results. Minus 1.85. This is minus 1.369. This is not as accurate, right? This energy is higher than that. So there is a natural ansatz role. So this another ansatz we use too local. This is not as good. If I want to, for example, increase repetition, let's say 4, I guess it will print out. Again, well, because I have more parameter because I'm doing the repetition before. So you see that this one improved, right? Okay, this is make when changing from red 2 to red 4, we have improvement. I think it's minus 1.83 something to minus 1.85. So you try it itself. Okay, the next final part here is using a filter function. It says sometimes the true ground state Hamilton is not of interest because it lies in the different symmetry. Okay. In this case, the NumPy eigensolver can take filter function to return only the eigenstate with the correct number of particles. Okay. So yeah, so this using the Gaussian force driver, load this. Yeah, I think they are doing the vibrational problem. So I think these three notebook are sort of related. The first one is the electronic, second one vibrational, third one is introducing the quantum one, and then the first part is electronic, and then this illustration is using the vibrational energy. Yeah. Okay, so the road light is about to turn off. Yeah, Gaussian force driver and basis. So you see this, right? Four numbers. Okay, and you have seen this, but this is without filter, and this is with filter. Okay, but this is only NumPy, so I don't know whether they have done that for the quantum problem. Okay, you can use with filter, without filter, and then compare. Okay, so ground states. Oh, so this one is almost zero, right? The vibrational energy. And this one with the filter is like 2,400 cm inverse. And okay, it's using the get default filter criteria. So I don't know exactly what the default is. Okay, it says here, check the number of particles is in different problem and can be used as okay. Okay, so I guess this is the end of this Qiskit-Nature. I don't have time to go into other parts, but this is really quick uh, for like 2/3 of the lectures. This one, I mean, looks sophisticated because the underlying theory is indeed complicated because you have to deal with electronic, nuclear, and some approximation to get the coefficient, and from that you you then deal with that using quantum computer. So if you can just say, okay, maybe I I can live it with I'm using a package to get these coefficient, one body, two body integral, then it's fine. You don't need to understand too much. You just need to know how to run and get these coefficients. Then you can set up a quantum problem. Once you get a Hamiltonian and you map to qubit, then you can do it with quantum computer in principle. Okay, any questions? Any questions? I introduced this so that if people are more interested in presenting this electronic structure calculation, then they can go look up and more. Okay, so this Qiskit-Nature.